and they did it in this learning program language called Turing, and they didn't have to know pointers, and they did much better. So pointers can be hard. All right? All right, so let's talk about, now what we're going to do is we're going to run through the various data structures and give you a quick how they're implemented. But don't panic because, again, we're doing this fast. And people are rustling. We're not done, are we? We go till 8. Oh, we got another. Yeah, we go to 10 to 9. So we're not done. Don't rustle yet. I see rustling, and I think, what's up? I got almost another hour of your life. All right. So we are going to do a quick how do you implement things. All right. How do you implement the position? In my book, it's a pointer. All right. So here, memory. How does memory actually implemented? Right. It's a bunch of cells that are physically silicon in hardware. Right. And they have addresses. So this guy's address is 2. So we store 2. Right? You either can think of this as an array that's indexed, or you can think about this as actual physical memory that has addresses. Right? So the address of this cell is 2, so I store 2, and that is a position or a pointer to this cell, to this memory. Right? Everybody got that? Then a linked list, right, has these pointers. Trees is all about pointers. Right? The assignment is all about pointers. Yeah? Oh, the whole course is about linked lists. It's about stacks and queues and trees. It's, I don't know. Look at, the whole course is about building things that look like this. Does that answer your question? Not really. It's like, wait for the entire course. Yeah? No. No, that's what we want to, it's a very good question. I want to distinguish between the node, here's a node, and the address of the node, right? Right, well, there's the contents. I guess a node, in this case, is a little box, and it has 2 things. It stores something, and it has an address of where it is. It has a position, right? So the position is the 2, right? The pointer is the 2. It's the address. While the E, which was the content, is the happy face. Does that make sense? Yeah, there's no E on the slide. Remember before we were talking about positions, right? And position, the little girl was a data structure, was a variable. And what does the little girl actually hold? The little girl is holding the 2. Yeah, it's the position. The little girl is holding the position. She's of type position, so what she has is the 2. And then if you ask for her element, then we get the E, which is the happy face. I would say the happy face is the object contents. The object's position or address is 2. The object's content is the happy face. And what is the object itself? It's this box that has an address and has a location. And God's contents. This one? Yeah, well, this record here is a node, right? And it's stored somewhere in memory, right? And it looks like they're a nice line here, but these could be anywhere in memory, right? This could be one place in memory, and this could be a next place in memory. One thing I know for sure is that this box and this box are next to each other in memory, because this is one node, right? What is a node? And I thought it was a mouse or something, but it was only a pen. Right? So in C, you would define a record which tells you the shape. I'm going to have this box. This box is going to have these various fields in it. Right? So this node, oh, where did it go? There we go. You know, this shape, this template, is going to be our node. And what does it contain? It contains some information, and it contains a link to the next one. Anyway, we're going to do all of this stuff again. Right? What we're doing is we're doing spirals, repeating things over and over again. All right? So now we're going to talk about lists again. How are you going to implement the list? Well, you could implement it as an array. Any problems with an array? What's good about an array? How long does it take to put something in a square? I'm going to say constant time. Right? Now, actually, in hardware, it probably has to do with log-in, fan-out, but let's not talk about hardware. Let's say it does it in constant time. What is hard to do with this poor array? Well, I can delete that face just by going backwards. Searching can be, well, yeah, if you don't know where things are, you can search. Well, I don't know. That's the user's problem, right? Our problem, could we insert a new square? No. Can we make this list longer? No. So those are our first problems. Our first problems is we can insert, but our problem is that it's of a fixed size, right? When you set this up, you have to say how big it is, and it's a fixed size, right? And that fixed size could be determined at compile time or at runtime, but either way it's fixed. Right? Now, we could have a new data structure called an extendable array, which allows you to somehow make bigger arrays as you need them. Right? So you think about how we're going to implement that. Right? And that's great, but the problem is, how do you insert something? Right? If we wanted to insert a new square right here, we'd have to shift everybody over. Right? And that's where linked lists come in. The advantage is, if I have a pointer to here, I can easily insert things. Right? Yeah? Yeah. Yeah, exactly. Same difference. Right? But here, if I have it, I can insert things, I can move things, right? You asked, why do we have linked lists? Here, so that we can help move things around. Right? Now if I have a spot here, I can insert something in how much time? Constant time I can insert a new guy. Right? But if I need to find somebody, then I got to walk there. Right? I specifically said I can insert somebody here if I got my finger there. Right? But if I have my finger here, then I'm in trouble. Right? Because I can't go backwards. Right? So, but to move around, right, can take you order in time. Right? Does that make sense? Trees, there's a tree. Let's say it's in a binary tree. Let's say you have in nodes in the tree. What's the height? Log n. Where do you get that from? Yeah. The depth. Well, one way of thinking about it is every layer doubles the number of nodes, right? I have one node, then two, and then four, and then 8, and 16, right? So the number of nodes is exponential in the depth, right? So the depth is logarithmic in the number of nodes, right? And you can also imagine as you take a step, you're kind of deleting half the tree. You take a step, you delete half the tree. So what is log n? Is if you take n and you divide it by 2, you divide it by 2, divide it by 2. How many times you divide by 2 to get to 1? Yeah? This is the height. Oh, yes. Yeah, so depth, height, same difference. I think one's coming down. One assumes you're at the root and you're going down. One's at the bottom. You assume you're, I don't know. Height, depth. Search time. So how long does it take for you to find a leaf now. Yeah, if you have directions as you know which way you're going, then that's log n, right? So that's great. So if you have a binary, if you're doing a binary, so a whole data structure we're going to talk about, if you haven't already, binary search trees where you know how to find a node. Any problems that can come up here? If I gave you an in-node tree, do you know that its depth is log n? If I gave you a tree with n nodes, do you know its depth is only, its height is only log n? No, it is binary. It might be a vine, exactly. Right? It could be unbalanced. Right? And remember we said there's a whole section of this course devoted to balancing trees. All right? So you don't want your binary search tree to look like this, because then, right, then searches become log order n time. Yeah? Yeah, because every node has two children, an empty node and the next node. Right? It's a tree. It's just not balanced. Right? Balanced. So we're going to have a whole field of balanced binary search trees. Right? And here's the topic of how do you balance them? Well, you rotate. You rotate things. So it lowers things and raises things to balance them. And once it's a balanced binary search tree, now all the operations take order log n time. Right? So that's nice. Right? Before, some were constant time and some were linear time. But now we traded everything off, so everything is log time. Stacks. How do you implement the stack? Well, here you can implement it in an array, right? So our loop invariant would kind of be here. Here they're stacked up. This is the top of the stack, right? If you want to push something, you go this way. You want to pop something, you go this way, right? We're going to do this again. This is really quick. We're going to have a whole section on implementing this, all right? So don't think that. Right? Queues, well, now you're adding on this end and removing from this end, so they're going to start rotating around, so we're going to put them in a circle. Right? Does that make sense? All right, we add this end, we remove this end, we got an array in a circle. Right? Or we can do linked lists. And if you're at this end, it's easy to add things and remove things, so it's a nice stack. And if you're a linked list, it's easy to arrive this way and to leave this way. You got to we'll have a whole section on how to do that. It turns out it's hard to have it leave from this side. So here's something you can think about. Why is it easy to arrive and leave at this end, easy to arrive at this end, but it's hard to leave at this end? Think about that. I want to delete this guy. Why is it hard to delete this? I can add a new object. Here I can add an object and remove an object. Here I can add an object, but it's really hard to remove an object. Yeah? And why do I need to go back? Well, I could just throw this away. Derive. Yeah, she's talking. Yeah, exactly. Yeah, so the loop invariant, the system invariant, says that the variable arrive is a position or a pointer pointing at the last guy, right? So deleting this last guy is not a problem, right? You can delete it. But if we want to maintain the loop invariant, we need to have the pointer pointing to the next last guy. And how do we find him? We have to walk around, right? So we're going to cover all of this in later slides, right? Priority queues, right? Remember what a priority queue is? Everything has a priority. You throw him in as priority. You give him a new priority. He moves up and down. You say, give me the thing with highest priority, and Marilyn Monroe comes out, right? So how do you implement it? Well, you can implement it in an array, but it gets to be hard to insert and find and write. You can implement it in a binary search tree, and remember all operations talk log in time, and that's good. It turns out that there's another thing called a heap, which is just, it's simpler than binary search tree has a lot of complicated overhead pointers and stuff. And in this case, this is all implemented in an array, and it's easier. So we use heaps to do priority queues. All right, and we have a whole section covering this. All right. Dictionaries. The dictionary is a word is associated with a definition, right? We talked about keys, right? So a collection of, if I have a set of everybody in this room, and I have a key which is your student number, right? Then we'd call that a dictionary because I look up your student number and I find everything about you, right? That's a dictionary. Yeah? Yeah, usually, yeah, there's less. I would say it's faster to code and probably runs faster because there's less overhead. Yes. Less. Here you're going to be allocating. Yeah, that's my sense. Anyway, people say you implement priority codes with heaps, and I think it's because the code's simpler and probably faster. But they're both order in time. They're both order log n. So if it's faster, it's the constant, not the. So how do you implement the dictionary? We talked about hash tables, right? We would take your social security number and throw it in a random place in the room in such a way that it's not really random, it's pseudo-random, so I could find it again, right? All right, what else we got? Graphs. All right, so here's a graph. A graph is a node. It has edges. The nodes have names. The edges can have names, right? How are we going to data structure to store it? Well, one data structure is a matrix. And we're going to have a row for each node and a column for each node, right? Here, a row for each. Sometimes I'm going to say node, and sometimes I'm going to say vertex. It's the same thing. So hopefully that doesn't confuse people, right? We have a column for each vertex, and then each entry then becomes an edge, right? You'll see E. What is E? E goes from U to V. So UV is E, but E is also at VU, right? People follow that? So that's an obvious data structure. We call it the adjacency matrix. We could also think about, obvious thing would be to have these as nodes and have pointers between them, right? So we could have some sort of linked list thing. Here, this could be a node, and it has the name of the node U, and then it has a pointer to V, right? So we could have something like that. But then it gets complicated because U has some number of children, links, right? So you have to say, how are we going to store all their links? And so we need to access, we have to quickly find these nodes, and we have to quickly find the list of edges for every node, right? So what we'll do is we'll have some data structure which is a list of nodes. And you can have that be any data structure you want. It's a list of nodes. And so you see here we have all the nodes, right? And for each node, right, for each vertex, we need to list the edges, right? So here, each node is pointing at a data structure that lists all the edges, right? And then you could also say here we have a list of the edges, and each edge then points to, each edge has two nodes, right? Right. So each E is between U and V. So E can point at U and then point at V. And then similarly, you could have a vertex list that is pointing at the nodes. Right? So we can build up various data structures like this. Are people kind of seeing this? Basically, you need, however you're doing it, you have a set of nodes, and you have to be able to move between those. And given a node, you have to find out what edges it's connected to and who are the nodes at the other end. Right? Or maybe there's a set of edges, and you want to look at various, I might want to iterate through the edges, or I might want to iterate through the nodes. Or given a node, I might know who its children, who its neighbors are. Right? Everybody kind of following that? Yeah, we're good? All right, so this is the summary of everything we just said. And again, I think, don't panic, I think that's the whole course again. Right, so we've done the course twice now. Yeah? Yeah?
So when we're talking about the maps and nodes, just in the last slide, would we ever, in a real life situation, simulate NFAs or DFAs using that sort of thing, or that's just not an application?
Oh, yeah, for sure. That's very much so. I mean, imagine I get on the telephone, and they say, I'm at a main menu where these are your options, right? So you're sort of, that's a node in the tree. I'm here, right? It's going to say, you're at this node, and I don't know if this is, it's sort of, yeah, it's a DFA. I'm at this node, and these are my options. And then the user pushes, I want option E. So it's kind of like the input to a DFA, right? And then what do? Is then it moves based on the E. The input E, it moves to the next node, right? And now the phone says, now you're at this menu, and these are your options. Does that answer your question? Everybody kind of follow what we're doing?